In this video, we're going to review energy and momentum of rotating systems. We're going to start by looking at how torque can transfer energy into and out of an object or rigid system if the torque is exerted over an angular displacement. To better understand this, we're going to first take a look at linear motion. So here we have a box and we push it to the right with a force F over a displacement of delta x. The amount of energy put into the system or removed from the system is equal to the amount of work that is done on the system. And work is equal to force times the displacement. If the force and the displacement are not in the same direction, then we use work is equal to Ft cosine theta. Theta is the angle between the force and the displacement. Now, the rotational version of this is work. The rotational work is equal to torque times the angular displacement. Torque is, as a review here, is r, the distance between the axis of rotation and where the force is applied, times the force, times sine theta. And theta is the angle between the r vector and the force. We can also use graphs to find the work done on a system. So let's start with a linear motion. So on a force versus displacement graph, the area under the graph represents the work done by the force. On a torque versus angular displacement graph, the area under the curve represents the work done by the torque. Next, we're going to take a look at angular momentum. First, let's review linear momentum. So when an object is moving linearly, it has momentum, which is equal to the mass times the velocity of the mass. Notice that both the velocity and the momentum are vectors. When an object is rotating, it can also have what's called angular momentum, and that is equal to the rotational inertia, also known as the moment of inertia, times the angular velocity. And notice that both the angular velocity and the angular momentum are both vectors. Now we're going to take a look at the angular momentum for a point mass. Previously, we looked at an object rotating, but an object moving in a circle can also have angular momentum. To calculate the angular momentum of a point mass, we start with L is equal to I omega. I is the rotational inertia. The rotational inertia for a point mass is mr squared. Angular velocity, omega, is equal to v over r. If we substitute the I and the omega, we get L is equal to mr squared times v over r. One of the r's will cancel out, and that will leave us with L equals to mrv. So the angular momentum of an object going in a circle is equal to the mass of the object, r, the radius of the circular motion, and times v, the speed of the object. That will give you the magnitude of the angular momentum. If an object is moving in a straight line, it can also have angular momentum. Imagine if there was a rod right here with a pivot at this point, and this was a clay ball, and this clay ball was moving and it hit the rod right here. Then this rod would start to rotate, kind of like a door. Imagine if there's a door here and there's a hinge. This clay, throwing a clay on this door will cause that door to rotate. So there is a relationship between the motion of this object here, even though it's moving linearly, with rotational motion. So what is the angular momentum of this mass moving to the right? Well, it's going to be L is equal to m, the mass of the object, times r, and r is going to be the distance between the reference point and where the mass is located. And this reference point is important because depending on where the reference point is, that's going to affect how much angular momentum that object has. V is going to be the speed of the ball, if you're looking for the magnitude of the angular momentum, times sine theta. And sine theta, that angle right there, is the angle between the r vector, or the position vector, and the velocity vector. So it's going to be that angle right there. Next, we're going to take a look at the angular impulse momentum theorem. To derive this, we're going to first look at the linear version of the impulse momentum theorem. We're going to start with Newton's second law, which states that the net force is equal to mass times acceleration. Acceleration is delta v over delta t, and if we move the delta t over to the left, I get F net delta t is equal to m delta v. And m delta v is the change in momentum, P final minus P initial. This quantity, F net times delta T, we call this impulse. And so the impulse momentum theorem basically states that the impulse is equal to the change in momentum. If the net force is equal to 0, then that means the momentum is going to be constant. It means the initial momentum will equal the final momentum. And this is super useful when we're dealing with collision problems. Now to the rotational version. We're going to start with the rotational version of Newton's second law, which is the net torque is equal to the rotational inertia times the angular acceleration. Now, angular acceleration is the change in angular velocity over the change in time. If I move the time to the left, the change in time to the left, I get the net torque times the change in time is equal to I delta omega. Now, I delta omega is telling us the change in angular momentum, and this value on the left here, which is the net torque times the delta t, that value right there, we call that angular impulse. So the angular impulse is equal to the change in angular momentum, and that's what the angular impulse momentum theorem tells us. Now, if the net torque is 0, then the angular momentum is going to be constant. And the angular momentum is constant, we can state that the initial angular momentum is equal to the final angular momentum. Now we're going to look at some graphical representations of things that we've been talking about, such as torque and angular impulse. But we're going to compare it to linear motion. On a momentum versus time graph, the slope represents the net force. On a net force versus time graph, the area under the curve represents the impulse. And this area can be positive or negative. On a angular momentum versus time graph, the slope represents the net torque. On a net torque versus time graph, the area under the curve represents angular impulse. And once again, this area can be positive or it can be negative. Now we're going to take a look at the conservation of angular momentum. Just as the conservation of linear momentum is super helpful for analyzing systems with multiple objects colliding and there's no external net force, the conservation of angular momentum is helpful when you're analyzing multiple objects and there's no external net torque. If there's no external net torque, then we can say that the initial angular momentum equals the final angular momentum. We can expand this equation out and write I1 omega 1 plus I2 omega 2 is equal to I1 omega 1 prime plus I2 omega 2 prime. Let's say we have these two disks here, and on the bottom white disk is rotating freely, and let's say that there's no friction. It's like a lazy Susan rotating platform and has a rotational inertia of I1. On the top is a disk that is not rotating and has a rotational inertia of I2. And we want to know what is their angular velocity once we drop the blue disk onto the white rotating platform. So the initial angular momentum is going to just be from the white rotating platform, which is going to be I1 omega 1 plus 0. And the blue disk has 0 angular momentum because it's not rotating. Equal to, and once you drop the blue disk to the white rotating platform, their combined rotational inertia is going to be I1 plus I2 times omega f prime. Omega f prime here is going to be their angular velocity. To find the angular velocity, we're going to multiply I1 plus I2. So we're going to divide I1 plus I2 on both sides, and we get that the angular velocity, once the top disk is dropped to the bottom rotating platform, is equal to I1 omega 1 divided by I1 plus I2. A common example used to illustrate the idea of the conservation of angular momentum is a figure skater. When a figure skater wants to start to spin faster, you'll notice that they'll start with their arms out real far, maybe with their legs out as well. And then when they pull their arms in, their legs in, you'll notice that they start to spin faster. So what is going on here? So angular momentum here is conserved because there's no external net torque. That means the initial momentum needs to equal the final momentum. But how do they spin faster? Well, when they stretch out their arms and their legs, they have a larger rotational inertia. When they bring their arms and their legs in, they have a smaller rotational inertia. So what's the trade-off? Since the initial momentum equals the final momentum, the trade-off is their angular velocity. So initially, they have a large rotational inertia, but a small angular velocity. When they bring their arms and legs in, they have a small rotational inertia, but a large angular velocity. Now we're going to take a look at rotational kinetic energy. We already know about translational kinetic energy, which is equal to 1 over 2mv squared. When an object is rotating, it can also have rotational kinetic energy, which is equal to 1 over 2 times I omega squared. I is rotational inertia times the angular velocity squared. The total kinetic energy of an object is equal to the translational kinetic energy plus the rotational kinetic energy. Let's take a look at a soup can race. We have these 3 cans. Can number 1 has very low friction coating on it, so it's not going to roll. It's just going to slide down. Can number 2 has thin soup. Only the metal outside part of the can is going to be rotating. The soup is not rotating. And can number 3 is thick soup. So not only the can rotating, the metal part of the can rotating, but also the soup is rotating. So which one's going to win? Can 1 is going to win because all of the gravitational potential energy has been transformed into translational kinetic energy. So it's going to be the winner. Can number 2 is going to be second place because some of that energy has been transformed into rotational energy. So some of that energy is needed to make it rotate, so it has less translational kinetic energy. It's going to have less energy to move it down the ramp. Can number 3 is going to be last place because even more energy is going into rotating the can because not only is the metal part of the can rotating, but the soup is rotating, and less energy is going to be available to move it down the ramp. Let's see how we can illustrate this race on a LOL energy bar graph. So on the left-hand side is the initial energy, and then on the right-hand side is the final energy, and the middle here is our system. So our system is the can, the ramp, and also the Earth. In order to have gravitational potential energy, the Earth needs to be part of that system. And initially, we have gravitational potential energy. And this is just qualitative. We're not doing any calculations, so the boxes are not going to be perfectly exact in proportion, but I think you'll get the idea. So initially, we start off with gravitational potential energy. As the can slides down, some of that energy is transformed into rotational kinetic energy, and some of that energy is transformed into translational kinetic energy. Next, we're going to take a look at rolling without slipping, and we're going to derive 3 equations to relate the motion of the center of mass with its rotational motion. When an object is rolling without slipping, a point of contact with the surface is momentarily at rest relative to the surface. This means that it's not sliding along the surface. It also means that the frictional force does not dissipate any energy. So let's say we have a hoop that is rolling. And let's say it makes one complete rotation. The displacement of the center of mass will equal the arc length. In this case, it would be the circumference of the hoop. And we know that the arc length is equal to r times the angular displacement. So our first relationship here is that the displacement of the center of mass is equal to r times the angular displacement. Our next equation, we're going to start with velocity. And we know velocity is equal to the displacement over time. We're going to substitute our equation that we just derived for the displacement of the center of mass and substitute that in over here. And so we get that the velocity of the center of mass is equal to r times the angular displacement divided by the change in time. And the angular displacement over the change in time is, by definition, is angular velocity. So the velocity of the center of mass is equal to r times omega. Next, we're going to look at acceleration. And by definition, acceleration is change in velocity over change in time. We're going to substitute the equation that we got for the change in velocity, and we get that the acceleration of the center of mass is equal to r delta omega over delta t. Delta omega over delta t is, by definition, the angular acceleration, alpha. So the acceleration of the center of mass is equal to r times the angular acceleration. Next, we're going to take a look at gravitational potential energy. Now, you might wonder why we don't just use MGH. And MGH is very useful if the gravitational field strength is constant, or if you're on the surface of the Earth and you know what the gravitational field strength is. But as you get further and further from Earth, the gravitational field changes, and we have to use a different equation, which is going to be this one right here: negative big G times m1 m2 times divided by r. And the big G is the gravitational constant, and that is 6.67 times 10 to the negative 11. Big M is the mass of the central body, such as a planet or a star. Little m is the mass of a smaller object, and r is the distance between the centers of the two masses. You might wonder why there is a negative here, and that the reason for that is because the gravitational potential energy is defined to be zero when the satellite is an infinite distance from the central body. So as you get closer to the central body, the number becomes more and more negative. And here's a graph to illustrate these ideas. So on the x-axis, you have r, how far away you are from the center of the central body. On the vertical axis, you have the gravitational potential energy. We're going to start at the center, on the surface of the planet, and as you get further and further away, you'll notice that the gravitational potential energy increases. However, what that means is that it's becoming less and less negative. Next, we're going to take a look at circular orbits. In a circular orbit, the following are constant. First, the gravitational potential energy is constant as the object goes around because the distance from the central body is constant. Next, the kinetic energy is also going to be constant because the speed is constant. And we know the speed is constant because there's no work done on the object because the force and the displacement are going to be perpendicular to each other. And then the angular momentum is also going to be constant because the gravitational force is always acts radially, so there's no torque. Now let's compare elliptical orbits to circular. In an elliptical orbit, the following are constants. The total mechanical energy is constant because there's no external net force. There's only conservative gravitational force acting on the object. The angular momentum is constant because there's no external torque. Gravitational force always points towards the center. However, the following are not constant. Gravitational potential energy is not constant because r is not constant. And the kinetic energy is not constant because the speed changes. So as this object is going around at this point right here, it's going this direction, there's a gravitational force this way. There is a component of the gravitational force that's in the opposite direction of the velocity. That's going to cause the speed to slow down. On the other hand, over here, there's a component of the gravitational force in the direction of the velocity. So that's going to cause the speed of the object here to speed up. Next, I would like to derive an equation for escape velocity, but before we do that, I would like to define escape velocity. So escape velocity is the speed of an object that an object must have to break free from a planet's or a moon's gravitational pull without any further propulsion and reach an infinite distance away with zero kinetic energy remaining. So now we're going to derive an equation for the escape velocity. We're going to do that by first setting the total energy at the start equal to the total energy at infinity. And the total energy at the start is going to be K plus U, the kinetic energy plus the gravitational potential energy. We're going to set that equal to K prime plus U prime. And so the scenario is, imagine you built a super strong cannon that could shoot a cannonball into space with a lot of speed. The question is, how much speed does that cannonball have to have so that it can fly off and escapes Earth's gravitational pull? And we're going to assume that there's no air resistance here. So the initial kinetic energy is going to be 1 over 2 mv squared. This v will be the escape velocity plus the gravitational potential energy of the cannon on the surface of the Earth, which is negative big G times big M, the mass of the planet, little m, the mass of the object, let's say a cannonball, divided by r, the distance between the cannonball and the center of the Earth, equal to, and this is going to be 0 on the right-hand side. That's kind of by convention how we typically will set our reference point, which is going to be 0 at infinity. And You'll notice that the m's will cancel out. If we move this to the right-hand side, the negative big G, big M, little m over r, move that to the right-hand side, the little m's cancel out, and then we have a squared here. We move the 2 over, we're going to square root both sides, and we get that the escape velocity is equal to the square root of 2 times the gravitational constant times the mass of the planet divided by r, the distance between the cannonball on the surface of the Earth to the center of the Earth.